Welcome to the Rich Report, a podcast with news and information on high-performance computing. Today, my guest is from Cisco Systems. We have Jeff Squyres. Jeff, how you doing today?
Good, Rich. How's it going?
Oh, great. You know, it's great to have you on the show. I missed you at Supercomputing this year, and I imagine they had you sequestered away in some whisper suite somewhere.
I did. Lots of customer meetings. I was in the Cisco booth a lot because we had our, big debut of the orderability and being able to actually get our ultra-low latency Ethernet product. Thanks for the lead-in for that, by the way.
Yes.
And it went over really well,
okay.
Actually.
So you guys did launch that. It's a orderable.
We sure did.
Oh, that's great. That's great.
Yeah.
Okay, well, actually, we're here today to talk about something I noticed. You did a blog post about OpenFrameworks. And I instantly figured out this is something I need to know more about. So thanks for coming on. And can you tell us more?
Sure. So it's actually a several-month-old effort. Well, here, let's just jump right into the slides here. So I'm going to go to the slide number 2. This has got a little bit of an intro to it here. So a guy by the name of Hefty from Intel started this effort a couple months ago, and I should probably also mention Paul Grun. He's been a partner in crime on this as well. But the idea is that this is a successor to the Linux verbs API. The verbs have been good for some things, and it's been kind of bad at other things. And us MPI implementers have been complaining about the verbs API for the last 10 years or so. And there are some well-known problems that I'll get into in a bit. Now that's not to say verbs got a lot of things right as well, but there are things, it's showing its age, it's got some problems, and some newer hardware is finding it difficult to adapt to the verbs model, because verbs is all about InfiniBand hardware and InfiniBand models, not about newer, more modern hardware and things like that. And also sometimes verbs just doesn't serve MPI's needs very well. And MPI is probably the single biggest consumer of the verbs API that there is. And there's also a desire, too, to be able to serve other communities, like the PGAS community and some of these other up-and-coming APIs and top-level network consumers and stuff like that. And so it just seemed to make sense, and I really credit Sean and Paul for putting all this together and start a conversation in the community about what do we need, how do we go forward, and if we're going to make a clean break, don't look at this as Verbs 2.0, but really a whole new API. Let's start over from scratch and do all the things right. Take all the stuff that we've learned from Verbs and the APIs that came before that, and let's do something new here. So in the context of that conversation, on the order of several weeks ago, maybe a month ago, Sean asked me, he said, "Hey, Jeff, can you go out to the MPI community out of a new low-level network API? What does the MPI community want?" And so what I did is I sent a lot of email to a lot of people that I know in the MPI community and the MPI forum mailing list, and I said, "Hey, we got this cool invite from the OpenFabrics group, and it's a working group within Frameworks, or at least that's what it's called today. The name might change because it's not very Googleable. But they're asking us, what do we want? And I got a ton of feedback. Let's look at slide number 3 here. Here's a bunch of people who replied to me, and this is only half. There's a bunch more here on slide 4. So I got an overwhelming response, which is really tremendous. And then we actually even had a WebEx with all these people, and we got a lot of feedback and a lot of discussion. And I kind of assembled all of the feedback that we got into this slide deck, and put it into a single cohesive story, which was actually quite a challenge. But and then I took this slide, and I'm in the process of presenting all these requirements to the OpenFrameworks group. So that we can design this new API to serve MPI well and take us for the next 10 years or something along those lines. And so that's where this all came from, and that's what these slides are about. Now, one thing that came out that was pretty interesting is that the MPI community said, "Hey, this is great. We would like this to be an ongoing collaboration." So this is going to be a pretty exciting effort, I think. So let's go up on to slide 5 here, and just a quick MPI overview without diving into too many details at the bottom. But just to kind of frame the discussion that's coming up here. So MPI is a very high-level abstraction API, right? So, for example, there's not even a concept of a connection. You just say, send this to number 38. And on the receiver side, you say, hey, receive that from number 17. And a miracle occurs and the data is transferred. It's not like you open a socket, send something down a socket, and close a socket. I mean, that might happen underneath the covers, but from the MPI API perspective, there's no concept of a connection at all. All the communication is reliable. There's no such thing as unreliable communication in MPI. If you send something, it's going to get there. It's not like UDP, for example. There are limited sets of things that are put in order, and so applications can basically choose what kinds of traffic they want ordered and what kinds of traffic they do not need ordered with respect to other traffic. So it's flexible that way. And MPI, I think, is pretty obvious from its name. The message passing interface is all about messages. It's not about streams. It's not about just sending bytes. I send 100 bytes and you got 48 bytes, so then you got to pull again and get the other 52 and stuff like that. You actually send a message so that if I send 100 integers, you get 100 integers. Now, the peer address in MPI is an interesting thing. It's actually kind of virtualized. We have this thing called a communicator that, for all intents and purposes of this conversation, is a group of processes. And in that group, there's a unique ordering of the process. You can say, hey, send number 17 out of that group. And that uniquely identifies one of the processes in that group. The targets are a process. It's not a server or a NIC or something like that. It's an actual user space process. Going up to slide number 6 here, a few more things. This is a few more things on the overview here. There's a couple of different modes of communication in MPI, right? So there's blocking and there's non-blocking. Blocking meaning that when I call this MPI send and when it returns, I can use the buffer again. And non-blocking means that, well, I have to check later that it completed, right? So start the send now and either poll or block waiting for that send to complete later. But there's a disconnect between the initiation and the completion of the action. Then there's also point-to-point communication. We have two-sided and one-sided modes inside of that. So by two-sided, I mean there's a send and then there's a corresponding receive. Whereas on the one-sided mode, it's more like a put or a get kind of operation. And that does not exactly map to verbs RDMA, but they are similar concepts. Then there's also collect. Broadcast is an easy one to talk about. One guy has a buffer, and at the end of the broadcast, everybody has a copy of that buffer. And then there's scatter and reduce and several others. There's about a dozen and a half collect. Actually, there's more like 24 nowadays after MPI 3. But I'm not going to go into the details of what there are. And there's several other modes, but these are the ones you hear about the most. And I should point out, too, that both point-to-point and collective operations have blocking and non-blocking corresponding actions. Now, asynchronous progress is very strongly desired / required. You can actually talk to different people in the MPI forum and get different opinions about whether it's required or not. I'm in the camp that asynchronous progress is required. And that's the idea that when I start a send, let's say I'm an MPI application, I say, hey, start a non-blocking send of this 1 gigabyte message or something. And then the application goes off and does fast Fourier transforms for the next 10 minutes. Well, that 1 gigabyte message should actually progress behind the scenes and not be dependent on the fact that I'm, off computing FFTs. It actually made the progress while I was doing other interesting things. That gives you the overlap of computation and communication. And the message buffers are provided by the application, right? So the MPI library doesn't necessarily provide the buffers, which means that the buffers are not special or registered in verbs parlance, which means that the buffer is pinned in memory and then registered with the NIC or the HCA. So when the application provides the buffers, the MPI layer has to figure out and do all the right things to make them special if it's necessary to talk on the network with that buffer. Let's go on to slide 7 here. The MPI, I think it's probably pretty well known, but just to level set with everybody, it's a standard, right? There's a group called the MPI Forum that maintains it. And that forum is represented by a lot of people in industry and academia and the research community and so on. And currently there is MPI 3.0 is the level of the standard that is released today. We're working on 3.1 and 4.0 these days. There are many implementations of that standard. There are both open source and closed source implementations of it. And generally, they don't care about interoperability, at least on the wire, right? So I don't need to have OpenMPI on one side of the wire and MPitch on the other side of the wire. Not too many people care about that. All right, let's go on to slide 8 here. This is to frame the context of the feedback that I got. MPI is a large community, and all those names that I had on the slides way up at the beginning, that's only a part of the MPI community who chose to respond to this feedback. It was a good-sized part, but it is by no means the entire MPI community. That community represents a lot of different viewpoints and a lot of different MPI implementations and a lot of different hardware perspectives. And you take the union of all that, and it was hard to put it into a single narrative because not all these viewpoints agree with each other. I mean, let's take, for example, here on slide 9, if I had a real rough categorization, I would say there are two camps, right? Those who want super high-level network interfaces, like, for example, they don't even want to see memory registration. They just want the underlying layer to handle it. And they want tag matching in the hardware. They want something like the PSM interface, which is the interface to the the Intel InfiniBand implementation, right? They want to just trust the network API to do the right things underneath the covers, right? And then there are those who want the low-level interfaces. They are like, oh, okay, yes, I see that memory registration is necessary, so just give me a good infrastructure to do it, and I will do it in the way that I want to do it. And more importantly, they want access to direct hardware capabilities. And this is where the individual vendors shine here, because everybody's hardware is different abilities and exposes different things in the user space. So these people who want low-level interfaces want direct access to the hardware, not just for basic sends and receives, but even for the more esoteric capabilities, and exploit that for performance reasons up in the MPI layer. All right, looking at number 10, this is me telling the Open Frameworks group, be careful what you ask for because you just got it, right? I mentioned way up in the beginning that I think it's really awesome that the MPI community wants this to be an ongoing, but I don't know if they know what they're getting into, because in the MPI forum, talking about software interfaces is what we do. And I think this is going to be a new level of collaboration for OpenFabrics, but I still think it's going to be tremendously exciting and tremendously interesting.
All right, and then here on slide 11, after we did a little audio technology change there, let's talk about the basic things that MPI needs in itself. And having said that, the first bullet here is a little bit of a misnomer, because I said that MPI needs messages. And that's not entirely true. I guess what I'm saying here is that MPI works best when the underlying network supports messages, because that makes it easy for MPI to deal in the same types of things. The abstractions match. Now, that being said, it's incredibly common for commodity HPC clusters to just use plain vanilla Ethernet, no special technology, just TCP, and that's based on streams. So certainly MPI can be implemented on streams. It's just a whole lot easier and more efficient when it's based on messages. Now, that being said, that leads right to the next point of efficiency. MPI works best when you have an efficient lower layer network API, more efficient than TCP, right? You want to allow for low latency for short messages, and have short messages be able to ramp up to high bandwidth very quickly, right? You want to have a super low number of instructions on both the sender side and the receiver side, from getting a packet to the wire and getting a wire, packet from the wire, and so on. We want to also enable what we call zero copy, which basically means no additional copy when you take a buffer from user space and put it on the wire, and vice versa. And similarly, I said before that MPI exports the exact same capability that I'm asking for here of separation of action initiation and completion, right? I want to start sending that giant message and go off and do something else, and have the network layer just handle the rest of the transmission for me. And likewise, I want to post or receive and just later come back and see that it's done. So if these abstractions match between MPI and the network layer, that really makes things a whole lot easier. Similarly, with the one-sided and two-sided semantics, right? If I have puts and gets and sends and receives supported by the network layer, that can make things a whole lot simpler too, including the atomics. Now, atomics are things like I want to send you an integer and have you add that integer to the value that's already there, not just replace the value that's already there, or maybe do some bitwise operations or multiply or some kind of arithmetic kind of thing. So atomics are quite useful, and if the network just natively supports them, that makes MPI's job a whole lot easier. And also, there's no requirement for the communication buffer alignment. So if, for example, an underlying network forced me to have 64-bit alignment of all my communication buffers, that might well require an extra move or an extra copy or an extra something to get the buffer 64-bit aligned, rather than just being able to send from where it already lived or receive. Now, if we look at slide number 12 here, another important aspect is the asynchronous progress when you have multiple consumers in the same process. It's becoming quite in vogue these days to experiment with multiple upper layer communication stacks for different parts of your application, right? And here, what I have on the slide shown is MPI and PGAS in the same process. Today, doesn't really work so well for most communication stacks, simply because MPI has one progression and PGAS has a different progression, right? And they don't really play well together. But if the underlying network layer had a combined progression engine such that when MPI makes progress on its message passing actions, it would actually also progress the PGAS ones or whatever the other upper layer consumer is, that might allow things to play well and play better than what they do today. Now, preferably, this happens via dedicated hardware rather than having some kind of progress thread, because when you have a progress thread, that can steal cycles from the main application, and users tend to get unhappy about those kinds of things. All right, so let's look at slide 13 here. Another requirement that MPI has today is that it needs to be able to scalably communicate with millions of peers. And I really do mean millions of peers. I think there was a fabulous quote from a colleague of mine at Argonne by the name of Jeff Hammond. He said, anything less than 3 million MPI processes is weak sauce. So that is kind of the state of the art today, is low numbers of millions of peers, and that number's probably going to go up a bit over the next couple of years. Now, we have to do a lot of tricks with the MPI, with the network layer to get to be scalable up to millions of peers, but we want the network layer to be able to handle that. Now, keep in mind, this slide is about requirements. So we're saying what we want. We're not saying how that should be implemented. So there's a critical distinction here, because a lot of people might say, well, wait a minute, you already can do that with things like XRC and shared receive queue. And yes, these are true. These are all the good things that enable us to do that. We're just merely stating or restating the requirement that we've got to be able to communicate with millions of peers for both one-sided and two-sided semantics, which actually creates some challenges even in verbs today. I don't think you could communicate repeatedly with millions of peers in any kind of performant way with RDMA. Like I said in the beginning, there were a lot of things that verbs got right. So let's talk about the things that MPI likes in verbs today, right? The fact that there are different modes of communication, reliable and unreliable, and there is scalable connectionless communication. It's called UD, or unreliable datagrams, and so on. These are very useful, and there are use cases in an MPI implementer's toolbox where every one of these things fits well, and so we like those a lot. We also like the concept of RDMA, right, which maps sort of well to the MPI put and get semantics. They're a little different, but they help quite a bit. And it also helps a lot with offloading from the main CPU onto dedicated hardware if your hardware supports such things. We also like the concept of RDMA write with immediate. What that means is that I'm doing a put to the other side, into a specific buffer. I'm putting it buffer 100, this 1 gigabyte message, but I'm also carrying a little bit of an out-of-band message that can be placed elsewhere that can, for example, say, hey, I just did this 1 gigabyte put to your message, so that the receiver of that put knows that something happened. We do want a bit more than what verbs offers us today, but that basic capability is nice. On slide 15 here, there's also a capability where we can send a message and it's a short, quote, inline message, and we get the buffer back immediately, right? So it actually just does a copy under the covers, or does an immediate send, or some way or another that we actually get the buffer back immediately. It's very nice, very fast, and very efficient. We also like the fact that there's 2 modes for completion of verb sending and receiving. You can poll, which is usually what's used for the lowest latency. You can say, is it done yet? Is it done yet? Is it done yet? And so on. And that works really, really well. But sometimes you're like, I'm going to go block. It's okay to go to sleep for a while. I'm going to sit on this file descriptor and just, you'll wake me up when that giant 2 gigabyte receive is all done, or whatever the operation is that you're working on. Both of those have use cases that are useful. We also like the ability that we can discover your devices and ports in a very systematic and pragmatic way, and say, get a complete map of all the verbs capable devices in the system. However, it is kind of tied to a specific model right now, and we would like to divorce that and get something a little more generic, because modern hardware is not exactly in that same hardware model. So we want something a little more generic. Scatter gather lists for sends are useful because a common task for an MPI implementation is to be able to send an MPI header and then the actual user message itself. And those are usually in 2 different parts of memory. So if we can just point to those 2 different parts and say, send that, and send that as one atomic message, that works out pretty nicely. And also, verbs has some form of atomic operations, but we would like to expand on that and do some new things. And I have some slides on that later. Slide 16 here. This is similar to a picture I showed earlier, that you can have multiple consumers in a single process. This is a little bit different than the point I was making before, in that I could actually have multiple consumers in the same library in the same process, right? So I could have handle A and handle B and handle Q, and they could all be part of, the MPI library itself. And if I do something with A, it doesn't necessarily affect Q. That's a very nice property to have. It's not just a global state library, it's a per handle library. Things like this are very important for thread safety and other just types of programming goodness. Slide 17 here, there's a bunch of restrictions that verbs does not place on us, and we like that. There are certain esoteric environments where all of your MPI processes have to come together during initialization and say kumbaya before the network layer can be set up. And not having to do that is a very, very good thing. Some HPC environments also require you to only have one executable. So if you've got one A.out, it has to be the same A.out on all across your HPC job, and verbs does not require that of us. We can have an A.out, a B.out, and a C.out, and they can all be together in a single MPI job. That's nice. Verbs also doesn't restrict the completion order versus the delivery order. That's very nice. It allows overtaking of things on the wire, and in certain cases, that's very useful to MPI. You might need to have a short message jump the queue, for example, if you're in the middle of a large message transfer, for example. Verbs doesn't restrict the source and target address. So like I can send directly to your stack if necessary. And that is very useful, particularly for short messages. Verbs also doesn't require a specific wire protocol. It does put some limitations there, which is a little annoying, but all in all, it doesn't require a wire protocol, and that's a very, very good thing. We're not looking for wire protocol compatibility here. Slide 18, keep going here. This is my last bit of things that MPI likes in verbs. The ability to connect to unrelated peers, kind of similar to what I said in the last slide there, that if you start up 2 MPI jobs independent of each other, they could connect and accept to each other like you can with sockets. And MPI actually provides that capability in the MPI. So letting verbs or having verbs allow us to do that is quite useful. Also, there is some protection, right? You can't just read and scribble on other peers' memory without their permission. So that's a good thing. That prevents bugs, and it also allows MPI to have a security model. Also, the ability to block while waiting for completion. But you assumedly want to do this without consuming host CPU cycles, right? You want to say, oh, I will wait here, and verbs will tell me when this giant transfer is all done, and I can, basically yield the processor to something else, so maybe a different thread or something like that. Quite useful. And then most importantly, or actually tremendously importantly, I wouldn't say it's the most important, but if a process crashes or is otherwise sloppy about cleaning up, the driver in the kernel and all that will clean it all up for us, and guaranteed, which is wonderful. Now, on slide 19, let's describe a few things that MPI wants as verbs improvements. Recently, there was an effort to try and add some more MTU values in verbs, and MTU values are all discrete enumerated values right now. And Cisco actually wanted to add 1,500 and 9,000, and after very, very long conversations, we couldn't for backwards compatibility reasons, and that was a giant problem. So in this new API, we would like to see MTU as an int, not an enum. Also, the specified timeouts. When you make a connection, we want to be able to say, hey, try that for this amount of time before giving up. Right now, the timeouts are not really settable. Or an alternative would be have a connection manager that does everything for us asynchronously, kind of like sockets. Sockets have real timeouts, and the kernel acts as a connection manager for you, doing all the handshaking underneath the covers and just giving you back the socket when it's all done. Having that in a new Fabric library would be great. And all operations need to be non-blocking, including stuff not typically associated with sending and receiving messages, like setting up an address handle. The canonical example for this is, well, what if I need to do a network ARP to be able to create that address handle? Well, that might take some time, and so therefore I don't want to have to block waiting for that. I want to say, hey, create that address handle, and I'll come back later and pick it up when it's done. Same thing for communication setup and teardown, and same thing for memory registration and deregistration. These are all lengthy operations that in verbs are blocking operations. We would like to see these as non-blocking operations in a new API. Now, on slide 21, a few more improvements. Today, when you specify the buffer and length to a verb send, you have to put that in a struct and then pass the struct. Well, we would actually like to be able to pass that directly as parameters, put them on the stack and pass them that way. This would avoid a few memory dereferences, which is a good thing. We also want to be able to query and say, hey, how many credits are left in this particular queue pair? Because what if this action I did consumed more than one credit, right? There's newer hardware these days where doing a send might take 1 credit, but doing an accumulate might take 2 credits. And so this idea of variable amount of resources consumed per action that you're doing, you might need to be able to query for that, and that's very useful. Central in the verbs API concept is this queue pair, right, where I have a send queue and a receive queue. Well, turns out you don't always need that. Sometimes you want to just have a send queue, and sometimes you just want to have a receive queue. Case in point, in the OpenMPI implementation on the Cisco US NIC device, we actually use 2 send queues and 1 receive queue. And so it would be nice to separate that into their disjoint concepts. On slide 21, we would like to see a completion at the target for an RDMA write. Right now, an RDMA write, by design, it was intended this way, it doesn't wake up the software at all on the remote side, or at least has the possibility of not waking up the software. That it could be handled completely in hardware, and the receiver would only notice it if they actually looked at memory and saw that their memory had changed. Well, we would like to get some kind of completion on there, which might be useful in a number of MPI implementation cases. We also want to have the ability to query if the loopback communication is supported. Not all verbs-based devices support communicating to processes on the same server. And so that would be nice to have a little flag somewhere that says that. Also, probably one of the biggest problems with the Verbs API is that it is basically a union of a lot of different APIs for different hardware. And not all the functionality is supported on all hardware. And it's kind of actually a disaster. The opposite end of the spectrum is MPI. MPI is supported everywhere. Everything is supported everywhere. And let's not say it's perfect, but it's pretty good. Such that MPI applications are actually very portable in terms of functionality. But verbs really is not portable in terms of functionality. You really have to end up writing to each separate different device, and that's fairly painful. Now, slide 22, another point that a colleague of mine brought up is we would like to see a better ability to determine the cause of errors. So it can be really difficult to determine why did that send fail. And there's a lot of different reasons for this, but perhaps all we need is some kind of string capability so that even the different hardware vendors themselves can pass a message back up and give a more detailed message on why a particular thing failed if it's queried or something like that. And this might only be useful for the implementers, not so much an end user thing, but it's still pretty important when you're trying to write that MPI and you're like, why on earth did that send fail? I don't know. So this is useful. Slide 23. Here, let's talk about the high-level interfaces. Way back at the beginning, I said that there was these two camps of MPI implementers, those who want high-level interfaces and those who want low-level interfaces. The ones who want the high-level interfaces, here's three ones that we could start talking about today. There's this concept of tag matching, which is, I'm not going to go in detail about what that is, but suffice it to say it's very similar in concept to MPI two-sided sending, when you have this communicator and a peer and another integer tag, and is this message that's incoming match exactly what I'm looking for? If that can all be done in hardware, awesome, or at least done down at the network layer somewhere. Then there's also MPI collective operations. There's been a couple of vendors recently who have offloaded MPI collective operations like reliable broadcast and reliable all gather and a few other things like that onto the hardware itself so that you can get progression of a collective operation, not just progression of a point-to-point operation. And there have been tremendous speed-ups there. That's really great. So standardizing some of those APIs could be pretty cool. And then remote atomic operations. And those get actually pretty tricky and subtle and difficult to talk about, but suffice it to say there's enough experience these days that it might be good to standardize a network layer on that stuff. Now, the big caveat on all of these is that the API community wants direct input on the design of these APIs. So that's going to be, I think, an ongoing area of collaboration and interesting stuff. Now, there are divided opinions here, like, must every hardware support all of these high-level interfaces? Or can your hardware say, oh, you can query it at runtime, and the hardware can say, no, I'm sorry, I don't provide the tag matching interface. Some in the MPI community say, well, you should have to emulate in software if your hardware doesn't. And some say, no, a runtime query that says I don't support it should be sufficient. So that conversation still needs to occur, but at least today there's divided opinions on it. And then on slide 24 here, I think this is one of the most important things. This is one of the things that I and Cisco are promoting, that we need to get down to vendor-specific interfaces. So having an upstream interface in Linux is really great, but if it only allows you to do the things that API defines, that's kind of limiting, and that's one of the problems we have with verbs today. Take, for example, my own Cisco USNIC interface. We have a lot of capabilities that we just cannot expose through verbs because verbs wasn't designed to expose our capabilities. And I know the same is true for other vendor hardware as well. It's not like we're in a unique position. The point is that the lowest common denominator API is not always enough. Sometimes there's more things you have in your hardware that somebody who designed the software API 3, 5, 10 years ago didn't think of. And so you need a way to be able to expose that. So really, we want to allow all hardware providers to extend all parts of the API wherever possible and say, here's what my hardware can do, and this is how you get to it from user space. So this is very radically different for verbs, and I think this is going to generate quite a bit of discussion in the community when we talk about this open framework stuff. We'll see where this goes. Now on slide 25 here, you'll see I could actually talk for another 2 hours on this stuff, but I think we've actually probably already stretched the limit of your slidecast here already today, Rich. There's a lot of cool stuff here, and it gets even deeper from here. So if you think this was complicated, this was actually the easy stuff.
Yeah.
But this is why we are MPI implementer. I mean, this is the whole point of why MPI exists, is that the chemical engineers and the scientists and the physicists, they don't care about all this stuff. They just want to do MPI send and have the miracle occur and get the data to the other side, right? They're working on their scientific problems, which I don't understand at all. So I can provide an MPI library for them to hide all this network junk underneath the covers and give them a nice, efficient way to send some data to the other side. So the point being, there's a lot more stuff here. And if any of your listeners are interested, I think we're going to attach the full set of slides on the slidecast on your website there, so they can see all of that. And more importantly, if they want to, please feel free to join us in the Open Frameworks weekly calls we have on Tuesdays at noon U.S. Eastern Time, where we're talking about all this stuff. We would love to have more people join us.
Well, terrific, Jeff. I really want to thank you. I know you presented this once already today to the Open MPI forum.
I did.
Forum. So I feel special, but I wanted to ask you about that slide you had about the two camps. And I just want to make the assumption that maybe the guy who doesn't have programming as his day job, he's a chemist or something, does he fall on one side? And the guys that want more granularity, are they more of the implementers? Or how does that fall?
No, that's a great question. It's not so much an end user question. These are different camps of MPI implementers, I should say, right?
Yeah.
But there is still a good coarse grain division here. The guys who want the low level interfaces are ones like me, right? The hardware providers themselves, the Ciscos, the Mellanoxes, and the other hardware providers. They want to expose their interfaces in the ways that they want, and then make MPI fit that. Or like we found, this one doesn't work, so let's try a different hardware capability to make MPI a little better. They want to have the flexibility to do whatever they want to do, right?
Yeah.
The other camp, the ones who want the high-level interfaces, are the MPI implementers who are not hardware vendors. The national labs, for example.
Sure.
And some of the research academics and things like that. They want to have a portable solution that works well across a variety of different hardware. And again, this is coarse grain and not entirely accurate, but if I had to roughly categorize the two groups, that's how I'd break it out.
Sure. And then, Jeff, this idea of the lowest common denominator for the API, so how do you as Cisco, when you come out with this new device and it's got these capabilities, how do you get at it as a programmer? Do you have to do something other than MPI to make that happen, or how does it work?
Yes, that's the thing, is that when we wrote the verbs device for our Cisco hardware, we were very limited. We could only expose the things that and then let MPI use that. But we've got 100 other capabilities that we're just chomping at the bit. I'm like, man, I wish I could expose this awesome capability of my hardware and let MPI use that, right? I could make MPI send be 17% better if I could use this other capability of my hardware, but I can't because verbs doesn't let me expose that, right? So what we're looking for in this new Fabric API is give me a way to generically expose any of my hardware capabilities. And yeah, at that point, you'll be writing code for a specific piece of hardware, but that's okay. You would query the API and say, this is a Cisco device, and look, it's got all the standard stuff that we provide, but look over here, here's another vector of Cisco-defined specific functionality that you can use if your application knows how to handle that kind of functionality. Go ahead and use all these extra function pointers if you want to. That's the kind of thing that we want to be able to expose. And again, I'm saying this with a Cisco voice, but this really applies to all the hardware vendors as well, because the lowest common denominator API that I'm referring to really today is verbs, but everybody's hardware can do so much more than verbs. We want to expose more than that.
Yeah, absolutely. So you talked a little bit about the reaction today. How would you characterize it? Is it what you expected, or are you pleasantly surprised, or what would you say, Jeff?
I have to say I was very pleasantly surprised when Sean and the entire group was genuinely interested and said, Jeff, would you please go gather this feedback from the MPI community, because we really want to know what it is you want. Because to be honest, I have been going to these OpenFabrics working group things for the past several years, and I actually gave up. I haven't gone in the last 2-3 years because I gave up saying this is what MPI wants, and you guys in Verbs are not giving it to me.
Sure.
And I got kind of disillusioned with the whole OpenFabrics group. But now, Sean is coming to me and saying, all right, look, we realize you're our biggest customer, MPI, so we need to know what it is you need. So let's do it. Let's do it for real this time. Let's gather the feedback and let's start designing and build something new that works well for all of us. And that, I think, was the great moment for me, and that was the most surprising and most rewarding. And as I've been presenting this stuff to them, I get a lot of very insightful and deep questions from the Open Frameworks group. They're like, oh, okay, well, what exactly does this mean? And da-da-da-da. And, we're having some very deep conversations about this, and I think it's great. It's very promising looking forward. This is going to take a while, right? This is going to take at least, if everything goes lightning speed, I would say a year, right?
Sure.
So it's probably going to be more than that. But from where I'm standing right now, it looks very promising, and we're very encouraged by that.
Well, Jeff, I wish you the best on this. It sounds like very worthwhile, and you got great people over there, like Paul Gruen, like you mentioned, and Sean Hefty. And boy, you put a bunch of smart people together with a common goal, and I'm sure you're going to get where you want to go. And I really want to thank you for coming on the show today.
Hey, thanks for having me, Rich. I think this is great. Thanks for letting me put the word out.
You bet. Okay, folks, that's it for the Rich Report. Stay tuned for more news and information on high-performance computing.